Thanks so much for watching my talk, and thank you to the organisers for inviting me to speak at the TESS Science Conference. I'm going to talk today about stellar age determination, and particularly with TESS, one of the most important modes of stellar age determination is going to be gyrochronology or rotation dating. So that's what I'm mostly going to talk about in this talk. I'm going to talk about the gyrochronology models that we use, and I'm going to talk about how we measure rotation periods from TESS data. I'm going to start with my conclusions so that you know the key takeaways from this talk. The first one is that gyrochronology or rotation dating, measuring the rotation period of a star and then inferring its age from that, is a promising work in progress. So this is a technique with a lot of potential, but we haven't yet refined the models in detail. We know in broad scale that stars spin more slowly over time, but we still need to figure out all of the details of the models. Secondly, TESS light curves actually provide us with a new opportunity to calibrate the gyrochronology models. But finally, it is still difficult to measure long rotation periods from TESS light curves. So care is needed there. And these are the three elements of the talk that I'm gonna focus on. So to begin with, what exactly is gyrochronology? So gyrochronology, again, is this method of inferring the age of a star from its rotation period. So TESS gives you an opportunity to measure the rotation period of a star. And if you have that, and you have an idea of its temperature or its color or its mass, you can apply a gyrochronology model and infer what the age of that star might be. And to do that, we use models like this one, which is one of Jen Van Seder's gyrochronology models. She also made this beautiful animation. You can use models like Jen's, which is a semi-empirical model, or you can use a purely empirical model to relate rotation period and temperature or color or mass to age. The reason why this works is because stars lose angular momentum over time through a magnetized stellar wind. And that means that they spin down over time, they spin more slowly, they move upwards in this plot of rotation period versus temperature as they get older, and they do so in a way that is fairly easy to predict. I say fairly because, again, in broad strokes, we know what is happening. We know that stars rotate more slowly over time, but in detail, the models aren't fully worked out for all types of stars. Let me show you a version of this plot that I've made that uses real data. So this is not a model now, these are real observations of stars compiled from stars with measured rotation periods and ages in clusters at the young end, and then this also includes stars from the with rotation periods from the Kepler spacecraft and ages from kinematics. So this again shows you that the rotation periods of stars really do lengthen over time. We know this to be true, this is established, known for decades, but in detail, we still need to figure out exactly how quickly stars of different temperatures spin down. So I'm going to go over some areas of gyrochronology where there is still a little bit of a question mark. Open questions in gyrochronology. So I'm going to use as a way of pointing these areas out, these open questions. I'm going to use this figure from Santos et al. 2021, which is a new sample of Kepler rotation periods, which expands previous samples. Again, I'm showing rotation period on the y-axis and effective temperature on the x-axis here. This figure is from Santos et al. 2021. And so I'm going to use this to point out where the models, gyrochronology models, are still actively being calibrated and adjusted. One area is this. So this is old, fairly hot, sort of sun-like stars, F and G stars, old ones that are rotating fairly slowly, perhaps sun-like stars. These stars we think are undergoing something called weakened magnetic braking. And this means that we think that their dynamos, their magnetic dynamos, are shutting down when they're getting old. And so they're not braking magnetically anymore, or at least not very efficiently. So for old stars of solar mass, if you have a rotation period for a G-type star, for example, that is a fairly long rotation period, 20 days plus, then you will probably want to use a gyrochronology model that includes weakened magnetic braking, like, for example, Jan van Seder's gyrochronology models. This is a different phenomenon than stalled or paused magnetic braking. These two things are sometimes confused. They are different. They affect different types of stars. Stalled or paused magnetic braking affect K dwarfs predominantly, perhaps also M dwarfs. It is a different physical mechanism. For these stars, they appear to have stopped spinning down temporarily, but then they are expected to resume spinning down as they get older. And the reason for this is thought to be these stars are undergoing a redistribution of angular momentum in their interiors. And this has been particularly noticed in clusters. So for example, these two clusters in orange and green, you can see the stalling phenomenon happening right around here, right in the K dwarfs, where these two clusters that are different ages, their rotational sequences are overlapping. And that is because K dwarfs are not spinning down as quickly as one would expect from simple stellar wind-driven magnetic braking. So that's a slightly different phenomenon. If you have a rotation period for a K dwarf and you want to know its age, you should use a gyrochronology model that includes stalled magnetic braking, like the models of Spada and Lanza-Farmer from 2020. Okay, another thing to point out in this diagram is something that's usually called the Kepler gap. This is a gap in the rotation period distribution of stars. You can just about see it, but I'll point it out. It's here, roughly. And this is, again, another phenomenon that's been discovered from measuring rotation periods from Kepler. The origin of this gap is not very well known. There are theories. It could be related to stalled magnetic braking, or it could be related to there are a number of other theories for what could be causing this gap. Then there's another gap. Again, this is confusing. There is another gap that is usually called the M-dwarf bimodality. It's not really easy to see in these data. These are field star rotation periods. The M-dwarf bimodality is easier to see in open cluster data or in the Mirth sample, Elizabeth Newton's sample of rotation periods measured for M dwarfs. This is a different gap. It has probably a different physical mechanism that is creating this gap. It is probably caused by a reconfiguration of the geometry of the magnetic fields of stars as they age. I would actually expand the circle a little bit to say that in general, gyrochronology models are not well calibrated for M dwarfs. So this is an active area of research. We need more rotation periods for M dwarfs with reliable ages in order to calibrate gyrochronology for these low mass stars. And then young stars, again, we don't have a very accurate gyrochronology models for certain types of young stars. And in particular, if you have the rotation period for a star that is, you think, young, it can be quite difficult to figure out exactly how young it is, because young stars tend to have quite a spread of rotation periods, typically from about 1 to 10 days. So the rotation periods of very young stars, sort of less than 100 million years or so, don't necessarily map one-to-one onto an age. So, and again, this is a place where the gyrochronology models are still actively being refined. So to put all of these areas onto the same axes, I would say that those areas in blue are areas where the gyrochronology models are still, again, being refined in detail. In broad strokes, we know what's happening, but in detail, you should use caution when using gyrochronology models. You should make sure that the gyrochronology model you're using is appropriate for the type of star, the spectral type, the temperature, and the rotation period that that star has. So we do have quite a ways to go. There's a lot of this diagram that is blue. We have a bit of a way to go before we have gyrochronology models that are applicable across the board, across the rotation period temperature diagram. But TESS could provide new data that allows us to calibrate the gyrochronology models in all of these areas. It could provide us with new rotation periods for many field stars, for M dwarfs, for stars in new open clusters and moving groups, for stars with astroseismic pulsations that are observable with TESS, for stars in binaries, for stars co-moving with white dwarfs. There are all sorts of opportunities that TESS provides that could allow us to calibrate the gyrochronology relations. But that really does depend on how well we can measure rotation periods of stars with TESS. Of course, we would need to measure rotation periods in order to calibrate gyrochronology at all. So in the next section of my talk, I'm going to address how we can measure rotation periods of TESS from TESS. So let me start with this figure from Canto-Martins et al. 2020, which shows a beautiful TESS light curve, which is a sort of perfect example of how rotation manifests in the light curves, in the TESS light curves of stars. So this is a star which clearly has some magnetically active regions on its surface, which means that it will have some perhaps dark star spots or bright plage and faculae, and those active regions are rotating on the surface of the with the surface of the star, which is creating some periodic or quasi-periodic variability, which we can use to measure the star's rotation period. And there are a number of different techniques for measuring the rotation periods of stars, including wavelet transforms, Lomsgagel periodograms, Fourier transforms, autocorrelation functions, phase dispersion minimization. There are a number of different techniques that are all getting at what is the characteristic period of the variability in this light curve. In this paper, Canto-Martins, the authors measure rotation periods of TESS objects of interest. And they measure rotation periods of a couple of hundreds of stars with TESS. Now, one thing to be aware of with any stellar rotation study, anytime you want to create a catalog of rotation periods with any survey, TESS, Kepler, K2, you have to vet your rotation period measurements. You can't just always accept, for example, the period of highest power peak in the Lomsgagel periodogram, because not every star shows clear rotational variability. In this paper, the rotation periods are partially vetted by eye. For large numbers of stars, and TESS will provide light curves for large numbers of stars, automated methods have to be used, and I'll show you why. So this figure shows, again, rotation period versus effective temperature for stars with Kepler rotation periods in gray. So that's the underlying distribution of rotation periods from Kepler. And then in red, that is the raw statistics that come out of a Lomsgagel periodogram. So these are points that are just the period of highest power in the periodogram. And you can clearly see that if you naively use these raw statistics, you are not just measuring rotation periods of stars, you are also recovering systematic trends. So it's really key to apply vetting. And this plot was created by Danielle Rowland, who works at the American Museum of Natural History, and she's working on developing an automated vetting tool for TESS, which is similar in spirit to the rooster algorithm developed by Breton et al. In 2021. So she uses a 3-step random forest algorithm to remove rotation periods that are likely to be incorrect and inaccurate. And when she does that, she reveals the underlying distribution of accurate rotation periods, which looks like this. So quite a dramatic change from the previous slide. There are a lot of incorrect rotation periods in there that are just reflecting the systematic signals in the TESS data. So this figure shows rotation periods that are, for the most part, expected to be accurate. And again, she's using an automated vetting technique that is a random forest-based vetting technique. So she puts a number of features of the light curves into a random forest algorithm and predicts which rotation periods are likely to be correct and which are likely to be incorrect. Let me just add the Cantor-Martin's rotation period to this plot. And I want to point out a couple of things from this ensemble of rotation periods. These are field stars. These are not predominantly stars and young moving groups or clusters. They are older stars typically. One thing that I want to point out is that TESS reveals a lot of rapidly rotating M dwarfs. TESS is observing more M dwarfs than Kepler did. So one of TESS's real superpowers is measuring rotation periods of M dwarfs. Again, these are field stars. They're not particularly young. They're probably older than 500 million years or so. And yet, a lot of M dwarfs are still rapidly rotating, even when they are field age. So what that means is if you have an M dwarf and you measure a rapid rotation period for that star, it's rotating quickly, you cannot necessarily assume that it is very young. We still don't know exactly when M dwarfs start to really spin more slowly. This is not the first time that these rapidly rotating field M dwarfs have been seen. You can also check out Tyler Gordon's 2021 paper, which is based on K2 data. He measures rotation periods for a number of rapidly rotating field M dwarfs in that work as well. Jason Curtis calls this phenomenon, calls M dwarfs the baby Yoda of stars. So meaning M dwarfs can look young, they can be rapidly rotating, but they're not necessarily young, just like baby Yoda, who I think is something like 70 years old, but he looks like a baby. One other thing I want to point out from these data is that long rotation periods clearly present a challenge. The Kepler underlying distribution of rotation periods shows that many stars rotate slowly, and yet the TESS rotation periods that we've measured so far are mostly shorter than around 13, 14 days. And that is partly because, a lot of these stars are just observed in single TESS sectors, so they only have 27 days of data. But it's partly also, some of these stars are observed in multiple sectors. So this is partly also that just sort of naively stitching TESS multi-sector light curves together won't necessarily allow you to get at the long period signals. You actually have to include long period astrophysical signals in your model at the same time as you detrend your light curve. So you have to model the astrophysical signal at the same time as the systematic noise trends. If you do that, you can actually preserve the long-term variability. So let me show an example of that. This is a figure from Soichiro Hattori's 2021 paper, he has developed this code called Unpopular. It's a causal pixel modeling based code. And he, in his method, fits the systematic signals and a long-term astrophysical signal, a polynomial model, at the same time. And he can show that this method recovers this beautiful supernova light curve really well. If you don't model the astrophysical signal at the same time, your astrophysical long-term signal will be wiped out. It'll be removed at the same time as the systematics. And so you won't be able to see it in the data. Soichiro is continuing to develop this method, Unpopular, a causal pixel modeling method, for measuring long-term periods. And that's what I'd like to show here. So this is a sample of stars that are observed both by ZTF, the Zwicky Transient Facility, and TESS. They're all M dwarfs, chosen because M dwarfs often rotate slowly. This shows the Zwicky Transient Facility period on the x-axis and the TESS period on the y-axis. Now, these TESS periods have been recovered from light curves that have been detrended using Unpopular, so a causal pixel modeling method. Sometimes we use a polynomial trend and sometimes we don't, and that really depends on whether the star is rapidly rotating or not. I can talk in more detail about this method if people are interested in the live session. But this figure shows that actually a lot of the time, Soichiro can recover the TESS rotation period that is a similar measurement to the ZTF rotation period. So we are fairly confident that a number of these rotation periods are correct, and a number of them are also long. These stars are rotating slowly. They're not all correct, and that is partly because these rotation periods have actually not yet been vetted. So despite not being vetted, it's actually quite impressive that the matches are so good, but it's partially also because Soichiro is still refining this model and optimizing it for rotation. I'd like to highlight another method that is designed to preserve long rotation period signals, which is called the TESS-SIP, the TESS Systematics Insensitive Periodogram, developed by Christina Hedges, which fits the systematic trends at the same time as a sinusoid. So it's like a Lomsgauger periodogram where you're actually marginalizing over systematic trends that are common between different stars. And she's able to demonstrate with this method that she can recover a 50-day rotation period for a star, TOI 700, which is known to have around a 50-day rotation period from ground-based assassin light curve. So this is another example of a method where you model the astrophysical variability and the systematic trends at the same time to preserve long-term variability with TESS. I would also like to highlight some projects that are using machine learning to predict long rotation periods from short light curves. So, for example, Kirsten Blancato has a method which predicts the rotation periods of stars from short, sort of 27-day light curves using a neural network method. Zach Claytor also has a neural network-based method that is designed to predict the rotation periods of stars from their TESS light curves. These methods are trained on simulated data or Kepler data and learn what light curves look like in a 27-day sector when a star is rotating more slowly than 27 days, has a period longer than 27 days. And then Lucy Liu also has a method which predicts long rotation periods of stars, which uses actually random forest. She combines a number of features of light curves and the stars themselves in order to predict these rotation periods. So these methods have a lot of promise for predicting long rotation periods of TESS stars, even if those stars are only observed in single sectors or non-adjacent sectors. But these methods still need training data. We need a large number of rotation periods measured directly from TESS light curves in order to have a large repository of reliable rotation periods measured with TESS data that we can use to train these periods. So we still need to combine machine learning with traditional rotation period measurement methods. So just to summarize, these are the areas in which we sort of need new data from TESS. We need stars of all rotation periods. We need rapidly rotating stars, slowly rotating stars of all different temperatures in order to really pin down the gyrochronology relations. And here are my conclusions once again. So gyrochronology or rotation dating is a very promising method, but it still needs refining in detail. TESS light curves could help us refine these models if we can measure rotation periods from them, but we still need to refine our methods for measuring long rotation periods with TESS. I'll leave it there. Thank you very much. I'll see you in the live session.